I'm audible properly. I'm audible properly to everyone. A very good morning to all of you. On behalf of Sardar Patel Education Campus, I welcome to one and all for this webinar. The topic of the today's webinar is probability and its application in mathematics. First of all, I would like to welcome our today's speaker, Dr. Aakar Roghelia, sir.
Thank you.
He is assistant professor in BBM Engineering College. He has total 16 years of experience. He has total 2 national and 9 international paper published and 7 national and 5 international paper represented. He has done Visharad in music field. He is very student oriented. As my personal review, he is very calm and he is ready to solve each and every problem solution for students. So, sir, please start your session.
Okay. Thank you very much, Premal Bhai. And once again, I am thankful to the SPEC authorities for giving me this opportunity of interacting with your students. And so basically what happens is that nowadays when we are going for this digital lectures, generally students are bored. So what I have started means I thought is that we will be starting this session with a small video clip, so that I hope that you will like it, and then we will actually go to the main things that we want to talk about. So let us first of all enjoy a small 2-minute clip. Okay.
Crossroads, a glorious day to see. When a cowpoke came riding up on a horse, looked down the road, called 3, stopping to think about someplace else. In probability, it was likely, yes, though it wasn't for sure, that this cowpoke must be 3. The sun climbed up to high noon. Another cowpoke said, gee, with an outfit like mine, it's certainly clear. It's unlikely I'll visit 3. A dry wind whistled. The cowpoke spun more than once to be on the safe side. But the answer was clear. This lone cowpoke down the someplace else road would ride. Then later that same afternoon, one mule from a mule team clomped in. One look at this cowpoke would make it quite clear. The 3's impossible spin. The spinner could spin all day, all night. One thing was easy to see. This cowpoke was headed to someplace else. But never, oh never, 3. As sunset arrived, one last cowpoke rode up, strong horse's back. The chances that 3 on the spinner would be were certain. That is a fact. Impossible clearly was not a word this cowpoke would ever use. A few quick spins made sure that 3, the only road to choose.
So yes, I hope that you have enjoyed this video. It is something related to some probability things, and it is a very basic things that is the video wants to talk about, like some impossible events, certain events, and all that. But before we go to that thing, uh, again, let us talk something about this probability. we have to talk about something, some basic things about that, and that is nothing but the. So here we are with that thing. So for today's lecture, we want to go for this. The very first thing that we want to talk here is a randomness. We want to talk about this randomness. Randomness comes in our life, in every day-to-day life, whether we are students of science or whether we are students of engineering or whether we are students of, we can say, technology. In all these fields, this randomness comes into the picture. And what we can say is the probability theory that we want to talk about. Probability theory is nothing but it is a phenomenon which is nothing but probability theory is, is a mathematical thing which will give the framework to this particular phenomenon. Now, when you want to talk about this thing, let us see some specific application of this probability. And the specific applications are nothing but, let us see this example. We'll start with a very simple example to begin with. And that simple example is nothing but our very famous example of flipping a coin. Because whenever we talk about this probability, always we talk about this particular experiment of flipping a balanced coin. That we talk always. So when you flip a coin, what happens? Yes, we know that there are only two possible outcomes that we get either head or tail. But perhaps if we know some more things means this information that I have is let us say that the force to flip a coin. We are applying this force to flip a coin. Second is, let us say it is the initial orientation. Third thing, the impact between finger and coin. Surface smoothness of the table on which we are flipping this coin. And let us say the material characteristic both things, coin and table. Okay, before actually doing this experiment, we have not thought of that with a very simple experiment like tossing a coin. We have this many things associated, but these are some of them. Still, we can say some turbulence in the air, or when the coin lands on what surface or at what angle. That type of things can be also added. So, if we know all these factors while doing this particular experiment of flipping a coin, then we can be sure that what will be our outcome. That is, whether it is a head or tail. But what happens is that we have all this information as absent. And since we don't have any information like this, we can't be certain about what will happen next, what will be the chances. And hence, what we do is whenever you toss a coin, we say that there are 50% chances of getting a tail. And same thing is for tail also. Or we can say it is a 1 by 2 chance. Actually, for probability, there are two common interpretations. We will come to the actual definition later on. But for probability, when you talk about the interpretation, two types of interpretations are there. One is it called with relative frequency. When you say with relative frequency means what? It says that when you toss a coin for large number of times, so when I say large number of times means what? That say for example you toss the coin for 1,000 times, then you toss the coin for 10,000 times, then we toss the coin for the lakh times. Then the proportions which comes that like head you get and tail you get will come closer. The proportion that proportion of head and tail both comes closer to 1 by 2. So that is one way of looking at the probability. That when you repeat that experiment large number of times, and of course your coin must be the fair coin. It should not be a coin that is used in solid. So as the number of flips increases in this case, the proportion will go closer and closer to the 1 by 2. So in that case, you have to repeat that experiment so many times. But that is also not feasible in some cases. So that is one of the interpretation of the, that is, let us say it is a number one. It is relative to frequency. And the second type of interpretation that we can have, second type of interpretation is a subjective, or we can say based on the personal belief of something happens. Say for example, I ask you a question that whether it will rain today or not. Whether it will rain today, then we will see according to the weather outside how many clouds are there, what type of information are there, or in earlier information of last year's or the humidity level. All this information is there, but again, this particular thing will differ. Means this is the second thing that we are doing is based on the belief. Last time this much humidity was there, this many clouds was there, then there was a rain. But some people don't believe that. So here you can have the different opinion by differently. We have different opinion by different people. So out of these two interpretations, sometimes what happens that by number one, when you find out the answer, when you say number one is this, or when you find out by number two, that is by belief way, then sometimes it happens that your answers match, but sometimes the answer do not match. So actually we have to give a particular definition that whenever you want to find out that thing, probability, therefore comes into the picture the basic definition, or we can say that the axiomatic definition. Okay, what is the axiomatic definition? When we got talk about that, that we will talk later. Again, we were not going into technicalities much. We will be just trying to see the mainly the application part. So before we go to the actual things like what are required for the probability, let me give you a simple experiment. I will take a simple experiment of now nowadays. Okay, and this is the current era of digitalization. So let us say that your mobile is there here. So this is your mobile device, and it is transmitting some signals. Okay. The transmitter is like here. So your mobile device will transmit some signals like 0, 1, 0, 0, 1, 0. Actually, what happens is whenever we speak something, whenever you are also seeing this particular video, but that is again transmitted through digitalization, that is through 0 and 1. So that everything is to be converted in 0 and 1. You are, I think, IT engineers and computer engineers, most of you. So you also understand this well. But what happens is this is to be received by something. So let us say that there is one mobile tower which is receiving. So this is our receiver. In this receiver, or we can say that instead of that letter, we can say that it is a mobile tower also. The received sequence that you are getting is like 0, 1, 0, 1, 1. So what happens here is that the fourth digit, this 0, is now transmitted as 1. And since it is transmitted like this, what happens is the actual message that you want to convey cannot be delivered over there. And this happens due to, actually this will not go like this, it will go like this. And that is what we can say is the main thing which comes into the picture is noise. Some of the words also you have heard in some other subjects also. And noise is a random phenomenon. We cannot predict that what kind of noise will be there. In this case, it is a fourth digit which doesn't go in a proper way, but always it is not like that. Sometimes the first digit will not go proper, sometimes the third digit will not. But then also we want that the whole message is to be transmitted correctly or with a particular precision. We are saying that okay, by this way, if you send, we will get 95% correct results. So how do we predict that? How do we do it? This is one of the applications of the probability. That, okay, if you want to remove some error here in this case, what is to be done? How you will go for that? Or what steps you have to take? That answers are given by the probability. That okay, you use this type of result. This probability theory is used extensively in this modern communication mainly. So this is just one example. You can pick up any discipline or any area in any subject. You can find out one of the applications like this because randomness is everywhere. Randomness is everywhere. Even we don't know that whether we are going to wake up tomorrow or not. That is also a Hence, probability is a powerful tool to understand and manage this type of thing. So now let us go to the basic things which is required to define the probability. I think all of you have done this because these chapters are already you learn from the very lower standards, like you started this from the schools. But then also, for the sake of completeness, I am taking all these things into the picture. The very first term comes here. It's called the experiment. So what is an experiment? This experiment is nothing but any phenomena or you can say any activity which we are considering is called an experiment. And whenever you do that experiment, when you do that experiment for single time, or you can say that single performance of that particular experiment, a very famous word is called trial. How many times you are doing that experiment, that is how many trials are there. And with every experiment, whenever you do, there is associated. Now we will again come to the mathematics part in a short while. Very famous thing, which is the simple. This is the very first word which comes into the picture whenever you want to talk about the world, and that is called the sample space. So what is a sample space? Oh, yes, everybody is right. All of you, whatever you think, it is nothing but set of all possible outputs. Since you know this, let me go to the very. I will take two, three small experiments, and we'll try to see the outcomes of that. Okay. So here I will be having my experiment, and here I will be having my sample space. So that later on, whenever we need that, we can talk about experiment number one, experiment number two. One, let us say a very famous experiment of rolling a balloon die. I Everybody has played Ludo in this pandemic so many times. So in die, we know that sample space, or let us generally we denote it by S. So the possible outcomes are 1, 2, 3, 4, 5, 6. All possible outcomes. If you do the experiment of let us do this measure rainfall daily. Say my experiment is like this, that measure the rainfall daily. In that case, okay, you think that okay, what kind of outcome will be there? Okay, but since it is a lecture, live lecture, I am just giving you the answer that it is x where 0 less than or equal to x less than equal to some constant k. Some constant k, that k is the maximum rainfall which occurs in that particular area. Or you can add some more number, a bigger number than that. Like here in Vidyanagar, say 20 each is average, then we can fix this k as to 30. So always the number will be between 0 to k. Because if there is no rainfall, we can say it is 0. For third type of experiment, checking a bulb. Checking a bulb means whether it is working or not. In that case, my outcomes are like this: effective and non-defective. Okay, this is for defective, and this is for non-defective. So better that I will try. So based on this, when you want to talk about, there are two types of sample spaces we have seen. This is the first case, like example number one and example number two. You can see that you can list down all the outcomes, and it will stop somewhere. Or you can say that that type of outcomes, whenever you are getting, that is called discrete sample. Example number one, Example number 3. In the second type of sample space that you have, the continuous type of sample space, which we have in our example number 2. As you can see that between 0 to k, it can take any value, and as it can take any value, it will go like that. Fine. And events are nothing but any subset of this sample space. Any subset of the sample space is called event. So next thing is of course the event thing. Event is subset of this sample space. And all these are sets. So whatever the procedure you can do with the sets like union, intersection, complement, all these things you can do with this also. Now I will quickly go to this definition. For that we need some basic words. So let us take very quickly. Next word we have is mutually exclusive. It's like exclusive showroom of Raymond or exclusive showroom of Paris. When you say exclusive means you will get only that particular thing over there. So here also we can see that two events are mutually exclusive, are mutually exclusive if one and only one of them ex- okay, let me take simple example. Rolling a die. When you roll a die, my one event is getting odd number, one event is getting even number. Whenever you roll a dice, what happens? You get yes, either odd number or even number. Both will not happen together. Next is exhaustive event. Exhaustive event. So exhaustive is a very famous word. Exhaustive means આપણે ઘણી વાર કહીએ છીએ કે okay, today I have was exhausted. I have worked so many hours. So when you talk about all possible outcomes and when you collect that outcome and if it gives you the sample space, when you combine that event and if it gives you the whole sample space, then this is called the exhaustive event. Like in case of tossing a coin, there is a one event of getting a head, another event of getting a tail. And A and B are called exhaustive because when you combine that, both the outcomes of the sample space are taken care of. Next thing we have is the favorable outcome. Any outcome which is a part of that event, like in this case, A head, in previous case, A head. If head comes, then head will be the favorable outcome. So if head will there, we will say that event occurred. Coming to the next thing, that is the equally likely. Equally likely event. When you say it is an equally likely event, or sometimes it is an equally probable event, that one of them cannot be expected in preference to the other. I will give just the example. I will not write the definition here. Say, for example, when you do this, roll a dice. What happens? Any of these six will come, and what are the chances of getting anything? Yes, we know that the probability is 1/6. So P of getting any X will be 1/6. So means everything is having. Okay, I'm using this word even I want to define that because already you know some of the things. So rolling a dice, every outcome has the same chances of happening. But the main thing comes here to define is the last word of your unit number 1, independent events. Actually, there is one more word like dependent events, but that we know. We are very much clear that the events which are not independent are called dependent. Two events are called independent if happening or non-happening of the first event, happening or not happening of one event will not affect the second one, happening or non-happening of the second. Very simple example I can give. For this, independent events are there or not. There are two events, event A or two events I'm doing. Event A I'm doing is I will select a card and put it back. And event B is also select a card by another person. But in that case, I'm not putting it back. So if what happens is that some person has, and I want to select a king. I want to select a king. So if the first person has already selected a king, but when he is putting it back, then there will be no effect on event B because same number of kings are there. But by chance, if we don't put it back, like in B, there is no specification. So B selected a card, but he is not putting it back. He is kept it in pocket. Then, if A wants to select a card, then again, yes, it will depend that what is the card he has got. That is what the independent and dependent. So, talking about all these things, now I can write the exact definition, actually the theoretical definition of probability. Okay. What is this definition says? In a condition as we always do a trial, so a trial result into an exhaustive, mutually exclusive, and equally likely cases. Exhaustive, mutually exclusive, equally likely cases. And m of them, m of them are favorable. M of them are favorable for happening of this event. Then the probability of E, as you know, is a favorable number of outcomes of total. So it is m by. This is how the probability is actually defined. Now, of course, on the basis of that, there are three axioms we have for the probability. So what are the axioms associated with that? Axiom number one, or I will say that I, the probability of any event A is always greater than equal to. Axiom number two, the probability of sample space S is always one. And axiom number three, if A1, A2, A3, and so on are these joint events. Joint event means there is mutual something common in that. Then P of A1 union A2 union A3 and so on will be same as P of A1 plus P of A2 plus P of A3 and again. This is how the three extremes are. We can talk about this the extremes in detail also, but I will take a little time to explain H of x. The first axiom says that the probability cannot be negative because the minimum chances that you have is it will not occur. Not occur means it is a zero. The smallest value possible is zero. It will never happen. That we can say. Suppose I say that if I roll a dice and get a head, okay, it will not happen. So that is the probability. The second axiom says that is this P of s equals to 1. That the probability of sample space, obviously it is 100%. And that's why it is totally to be 1. Why? Because whenever you do any experiment, any event happens, then it is a subset of the sample space. So any outcome which comes will be the favorable outcome. In that case, we can say that event happens. S always happens. So any outcome belongs to S. And so it is a sure, we can say, or otherwise we can say sure event. Rolling a dice, anything comes, we can say that yes, we have got the sample space S. So P of S is 1. But the third is very interesting. This third event, third axiom is a very nice or interesting event. Axiom. When the events are disjoint, means there is no overlapping between them, then the probability of that union will be same as the summation. Another way is to think that imagine that the probability of set of the areas. Say for example, let us look at this in terms of the Venn diagram. There are these events, and since they are disjoint, it will be like this: A1, A2, A3, A4, A5, and so on. So in our sample space, we have this many events. And probability is nothing but the area of that circle, suppose we talk about. And what happens that when you take union of this A1 to A5, then area of that and summation of the area of that will be same. So that is the interesting part which is coming for this axiom number 3. And based on this axioms, if you find out the probability, then always we will get the nice thing. Okay. So again, before I go further to this part, I will again show you one video so that it will be again that is a video. I will stop somewhere. You try to think that whether it is happening, whatever is happening is the way it should happen or not. Let us see.
You
Let me share that video with you. Okay, I will. What I will do with this video is that at some places, I will pause this video, and whenever I pause this video, you try to think that what you will do. Okay.
and a fellow castaway are stranded on a desert island.
Sorry.
You and a fellow castaway are stranded on a desert island, playing dice for the last banana. You've agreed on these rules. You'll roll 2 dice, and if the biggest number is 1, 2, 3, or 4, player 1 wins. If the biggest number is 5 or 6, player 2 wins. Let's try twice more. Here, player 1 wins. And here, it's player 2. So who do you want to be?
Okay. So in this experiment, what they are doing is that when they roll the dice, what happens is 1 to 6, any outcome will come, and when any outcome will come, if 1, 2, 3, or 4 will be the higher number, then player 1 will win, and 5 and 6 player 2 will win. So actually, there are 4 things where player 1 will win. So that is the question they are asking. That who you want to like be? Like you want to be a player 1 or you want to be a player 2? Okay, let us see the answer also over there.
First glance, it may seem like player 1 has the advantage, since she'll win if any one of 4 numbers is the highest. But actually, player 2 has an approximately 56% chance of winning each match. One way to see that is to list all the possible combinations you could get by rolling 2 dice, and then count up the ones that each player wins. These are the possibilities for the yellow die. These are the possibilities for the blue die. Each cell in the chart shows a possible combination when you roll both dice. If you roll a 4 and then a 5, we'll mark a player 2 victory in this cell. A 3 and a 1 gives player 1 a victory here. There are 36 possible combinations, each with exactly the same chance of happening. Mathematicians call these equal probable events. Now we can see why the first glance was wrong. Even though player 1 has 4 winning numbers and player 2 only has 2, the chance of each number being the greatest is not the same. There is only a 1 in 36 chance that 1 will be the highest number, but there's an 11 in 36 chance that 6 will be the highest. So if any of these combinations are rolled, player 1 will win, and if any of these combinations are rolled, player 2 will win. Out of the 36 possible combinations, 16 give the victory to player 1, and 20 give player 2 the win. You can think about it this way too. The only way player 1 can win is if both dice show a 1, 2, 3, or 4. A 5 or 6 would be a win for player 2. The chance of one die showing 1, 2, 3, or 4 is 4 out of 6. The result of each die roll is independent from the other, and you can calculate the joint probability of independent events by multiplying their probabilities. So the chance of getting a 1, 2, 3, or 4 on both dice is 4 out of 6 times 4 out of 6, or 16 out of 36. Because someone has to win, the chance of player 2 winning is 36 out of 36 minus 16 out of 36, or 20 out of 36. Those are the exact same probabilities we got by making our table. But this doesn't mean that player 2 will win, or even that if you played 36 games as player 2, you'd win 20 of them. That's why events like dice rolling are called random. Even though you can calculate the theoretical probability of each outcome, you might not get the expected results if you examine just a few events. But if you repeat those random events many, many, many times, the frequency of a specific outcome, like a player 2 win, will approach its theoretical probability. That value we got by writing down all the possibilities and counting up the ones for each outcome. So, if you sat on that desert island playing dice forever, player 2 would eventually win 56% of the games, and player 1 would win 44%. But by then, of course, the banana would be long gone.
Yes, so this was the story of the last banana. But once again, let us come back to that. So sometimes what happens is we think that something is happening, but actually that is not happening. So what you have to do is we have to go for the actual things that comes here. So let us now see to some theoretical part. The very first thing comes into the probability thing is generally counting. In counting, what happens is more people are making mistakes while doing this counting. Like in the previous one, that player one or player two, you can think of that player two will not have more chances. So how to count? How to count? For that, there are of course some things, some theorems are available. But, let me give you a simple example for that. There is a machine, and that machine can be like this. That operation wise, if you see that machine, there are three possibilities. It is easy to operate, or it is average to operate, or it is a difficult to operate. So that is one way we can rate this machine. Second thing is the price wise. What is the price of that machine? Either it is a expensive or inexpensive. So these are the two ways we can. And third is the maintenance cost of handling that. Again, maintenance cost also comes into this three parts. That it is cheap to repair, it is average to repair, and it is costly to repair. So how many ways we can rate this machine now? If there is a question, these are the three only possible things just now I've seen. Then you can choose anything like this, that it is easy to operate, it is expensive and cheap, or you can choose that it is difficult to operate, inexpensive and average, or what you can do is again difficult, it is expensive and costly. So this way actually you have to list down all the outcomes. But if you do like this, then what happens is these are just three possible things. If there are more things than what to do for that. And there are some theorems available for counting. Of course, and that theorem says that, of course, in this case, let me tell you the answer. That this can be done in three ways, this can be done in two ways, and this can be done in two ways, three ways. It is 3 into 2 into 3. So totally 18 ways are possible. Means there are some theorems. It says that if there are some events A1, A2, up to AK, and that contains N1, N2, Nk elements. So these are the sets in which you have N1, Nk elements. Then I want to select one from A1, one from A2, one from AK. That is what we want to do. Then number of ways are N1 into N2 into N3 up to N3. If one thing can be done in three ways, two ways, and three ways, that is what we have just now seen in the previous example. 3 into 2 into 3. Again, one more thing which is there is the permutation. Permutation is nothing but the rearrangement of something. So when you have n things and you want to arrange all of them, when you arrange all of them, how many ways are possible is actually n factorial ways. But generally what happens that when you have n things, you don't want to take all the things. You want to take some less things. If there are n things, then you want to take k at a time. Out of n things, you want to take k at a time. Okay. When you see that k at a time, here also there are two possibilities. Like when you select the card, just by seeing we are replacing. Here also there are two possibilities. Repetition and without repetition. Repetition and without repetition. So when you say that it is a without repetition, the chances are n p. P is for permutation, that you know. But if it is a repetition is allowed, then the total chances are n raised to. But sometimes what happens is some of the things are similar, similar. Similar, similar means like the next one. Let me take a word. Suppose my word is rearranged. I want to rewrite this word in any order. How many ways it is possible? Then of course we will count that how many letters are there. Total number of letters are 9. But some of the letters are like this. Are sorry. Some of the letters are like this. R, R. It is repeating. Similarly, A is also repeated. E is also repeated. So if you replace these two R's, if you replace these two R's, it doesn't make the new word. It will have the same thing. If this kind of thing is there, and you want to do the permutation, then what is this? How to find out that? So for that also we have a result, and that result says that if n things are divided into C classes, so that in every class you have same things, right? C classes. Then total number of permutation will be actually n factorial. But since you replace like RR, you have to divide by something. And that is n1 factorial, n2 factorial, nc factorial. Like in this case, rearrange. How many permutations are possible if you want to find out the number of permutations? What to say? It is nothing but 9 factorial as 9 words are there. But R is repeated 3 times, so it is 3 factorial. A is repeated 2 times, so divide by 2 factorial. Again, E is repeated 2 times, so it is 2 factorial. Remaining things are repeated only one time, so you can write 1 factorial, 1 factorial. But it doesn't make sense. So totally, if you count, it is a 1, 5, 1, 2, 0. Otherwise, it is a 9 factorial. How much is it? It is a large number. Okay, and that happens in that case of that select the balls, like you select red ball, white ball, yellow ball, because all the red balls are same. So you can select any of that. There is no number on that. So that is how when the things are divided into this format. But this is just by arranging. Sometimes arrangement doesn't require, and we require the combination. And in combination also, in combination, of course, what you do is n things are there, and you take k at a time. K at a time. Out of n, you have k at a time. Again, I will take the same two cases. When I say same two cases means repetition and without repetition. So if repetition, without repetition, it is a very nice thing. It is nothing but NC. But if it is with repetition, then the total outcomes are n plus k minus 1 c without with repetition. This many combinations are possible. I think we can take one small example. There is a one cafe, one hotel is there. In that hotel, what happens is you are seeing the menu, 4 sweets, 6 vegetables, 5 desserts. Okay, just we are seeing this method. 4 sweets, 6 vegetables, 5 desserts. Okay, okay. Everything else is also having some more choices. But say, for example, we have this many choices, and you want to select a meal. Your meal must contain 2 sweets, 3 vegetables, and 2 desserts. So how many ways it is possible? Then your combination will come into the picture. That this can be done into 4C2 ways. This can be done in 6C3 ways. This can be done in 5C2 ways. And of course, multiplication, multiplication, multiplication. And that gives the answer. Total 1200 ways you can select this. See, only this much. And you now think of this menus that we are seeing in the hotel. Okay, so many things are there. So how many combinations are possible? That's why the hotels are saying that yes, we have the 1,000 items possible. Because like this, if you take the combination, it will be that form. Now coming to the next thing, which is talking about the conditional probability. Conditional probability, because that is also an important word here. And there are two events A and B, and out of that two events A and B, one of them has already occurred, and we want to have the chances of the other. One has occurred or not occurred, we don't know. And we want to find out, let us say one has occurred, means say B occurred. And we want to find out P of A given B. That is called the conditional probability. Already B is given to you and you want to find out probability of A. You have to find out that, okay, for that also theorems are available. And as we are not going into the proofs of the theorem, let me tell you that whenever it is a P of A given B, you want to find out. It is read as P of A given B. The same as P of A intersection B divided by P of. And similarly, P of B given A you can find out. Of course, here the condition is that P of B is positive. If it has occurred, then only we can talk about it. This particular information will give you the uh, information about the dependent or independent event. That whether the events are independent or not, that you can check. Very simple thing we can say that P of A given B is same as P of A. If B is there or not, it doesn't affect on it. Then A and B are called independent. Or what you can check is P of B given A. And both the conditions you have to check. Then they are independent. Otherwise, they are dependent. Whenever they are independent events, we can say that P of A intersection B will be same as P of A. Even you can check this condition as well. Yes, it will be independent event or not. We'll try to see one example by taking a simple example and try to see whether the events are independent or not. That we can check or not. Right? So let us try to think that way. Card we select. Okay, there are 4 cards. Okay, I'm just taking 4 cards only. Diamond 10. Of course, this is a red color card. Card 8. It is also a red color card. Pair 10. It is a black color card. And 6 of this. It is also black hole. So out of these 4 cards, I want to choose. There are 2 events. One is event E, one is event F. Event E is this. Select a red card. Event F is select 10. Now you see that these are the 2 red cards. These are the 2 black cards. Event E is select a red card. My first question is this. Whether E and F are mutually exclusive. Of course, the answer is not. Because E and F both can happen simultaneously if you select this card. This is the answer that I have got. Second, if I want to say that E and F are independent, of course, you have to check E of E into intersection F. Like this, we will find out first of all P of E. P of E means P of 10. Sorry, P of E means P of red. How many red cards are there? 2. So it is a 1 by 2. P of F means P of 10. How many 10 cards are there? There also 2. Out of 4, it is 1 by 2. P of E intersection F means it is a red card as well as 10 card. There is only 1 card out of 4. It is a 1 by 4. And you can see that P of E intersection F equals to P of E into P of F. Because they are independent. So this is how we can check that whether the events are independent or not. Right? And for conditional probability, we have one theorem. Now sometimes we think that things will be like very simple. One theorem is there that is known as Bayes theorem. I will talk about that now, and I will take a simple version of that for only 2 events. So let us have V1 and V2 are 2 mutually exclusive events. And some probabilities are known to you, like P of V1 is given to you, P of V2 is given to you, P of A given B1 is also known to you, and P of A given B2 is also known to you. And you want to find out P of B1 given A. Okay, that is not available, but this is you want to find out. And Bayes theorem will help us. It says that it is a P of B1 into P of A given B divided by P of B1 P of A given B1 plus P of B2 P of A given B2. This is how the Bayes theorem will be there. And of course, you have done so many examples of that. But okay, so I'm not going to take any example of that. If this is for 3 events in the denominator, you have 3, 4, 5, as many things are possible. But let me start with once again. The lecture which I have started with is the signal. So when you process that particular thing, transmitted 1 and received as 0. Let me consider that once again. So probability of transmitted 1 will be received as 0, and probability of transmitted 0 will be received as 1. Say for example, this is some number, a small p, this is also small p. This now I'm not giving any value. It is a small p. two type of system I am doing for sending the signals. Now, what the mobile companies are actually doing, that is what I am telling you. This is the application thing that you have. There are two schemes I am going for. Scheme number one and scheme number two. In scheme number one, what I will do is I will send a single digit. In scheme number two, a group of three, or let us say that three-digit scheme. Single digit scheme and three-digit scheme, what happens in single digit scheme? Whenever I want to transmit one, I will transmit one. But in three-digit scheme, what happens is whenever I want to transmit one, instead of that, I will send 111. Clear? Single digit 1 1 and three-digit scheme 1 1. What happens here? When you receive one, obviously you will consider it to be one. But when you send 111, what happens is chances are that you can receive anything. So what is at the receiving end? Either of 111, 110, 101, 011 will be considered as one. At the receiving end, majority rule will be applied. Majority means out of these three numbers, if two are one, then we consider that to be one. So which scheme is good? Let us try to see that also in both ways. In single digit scheme, of course, the probability is like P. We consider this P means sending a wrong digit. It is considered a very small probability of 0.01. 0.01 means only 1% chances of getting incorrect answer. In three-digit scheme, what happens? What is the probability of getting a correct result that you want to have? So let us say when I am sending one, it will be received as one. What is the probability? It is 1 minus p. So just now I am sending 111. So it will be received as 111 will be 1 minus p into 1 minus p into 1 minus p. But it can be received as either 110 or 101 or 011. So either of these three outcomes, when I want to say 110 or 101 or 011, what is the probability? That one of them is incorrect, so it is a p, and other two are correct, means it is 1 minus p1. And this is happening for three times, so I can say this is 3p times 1 minus p1 minus. So my total probability of getting 1 as a 1, transmitted 1 will be received as 1, will be nothing but probability 1 minus p the whole cube plus 3 times p into 1 minus p into 1. Now here what happens? The getting correct answer is 0.99. If I put p equal to 0.02, the correct answer is 0.98. If it is 0.05, the correct chances are 0.95% chances. While in our case, if you put that formula here and try to find out for p equal to 0.01, this probability turns out to be 0.9997. Much better than that 0.94. In case of 0.02, this probability comes to be 0.9988. And in case of 0.05, it is again let us say 0.9920. So it is a much better thing that you are getting. So three-digit scheme will be good. So that is what the companies are doing. And yes, of course, before leaving this thing, again, I would like to show a last video of Base Village. And after that Base Village video, I think we will stop. So what is this Base Village is? Let us see that video. So since I am thinking that Base Village is because Bayes theorem. So let me share the screen once again. Yes, here it is.
The town of Bayesville has a population of 2,000 people. Jimmy is worried after reading a news article about a disease called conditionitis. Conditionitis is a serious but rare disease afflicting 1% of the population. Let's represent healthy people as blue and diseased people as orange. Jimmy decides to go to the doctor to get tested. Unfortunately, Jimmy tests positive for the disease. In other words, the test says that he has conditionitis. We will represent positive test results with yellow hats.
Could the test be wrong?
Well, the test is 95% accurate.
What does this mean for Jimmy? Note that there are two ways this test could be wrong. A person could test positive for the disease when they don't have it, or they could test negative when they do have the disease. There are also two ways that the test could be right. A person who has the disease could test positive, or a person who does not have the disease could test negative. Suppose that 95% accurate means if a person has conditionitis, then 95% of the time they will test positive, which would be the correct diagnosis. If the person does not have conditionitis, then 95% of the time they will test negative, which again would be the correct diagnosis. In other words, there is a 5% chance of misdiagnosis in each case. Given this information, how sure are you that Jimmy has the disease? A, he almost certainly has the disease. B, he probably has the disease. C, it's about 50-50 whether he has the disease. Or D, he probably does not have the disease. Let's imagine that we conduct the test for every single person in Bayesville and assign each person who tests positive for conditionitis a yellow hat. Recall that healthy people are represented as blue, diseased people are represented as orange, and a yellow hat represents a positive test result. Since the test is not 100% accurate, some of the people who get hats probably don't actually have conditionitis. The combination of the test results and the true disease status classifies our population into four groups. True negatives, or healthy individuals who are correctly tested as negative, true positives, or diseased individuals who are correctly tested as positive, false negatives, or diseased individuals who are incorrectly tested as negative, and false positives, or healthy individuals who are incorrectly tested as positive. If we just look at the negative results, our test seems pretty good. After all, it only missed one diseased person. However, looking at the positive test results, we find that a large majority of the positive test results are actually false alarms. This is good news for Jimmy. His positive test result does increase his chance of being diseased, but with so many false positives, it turns out that there's only a 16% chance he's actually sick. There's an 84% chance he does not have conditionitis. So Jimmy stops panicking, but decides to get a second opinion, just in case. Did you make the right prediction? In general, we need to take into account the rarity of a disease, not just the accuracy of a test. And we need to distinguish between the probability of having a disease given that you test positive and the probability that you test positive given that you have the disease.
Yes. Okay, so with this positive video, I would like to say that stay safe, stay healthy, and all the best for your future.
Okay, sir. Finish.
Yes, yes.
Okay, very much. Thank you, sir.
Thank you very much.
First of all, I would like to thank you, Dr. Aakar Roghelia, sir, for your wonderful session. It was very informative session. And also, I would like to thank you, our chairman, sir, Sri Girish Patel, sir, secretary, sir, Sri Sital Patel, sir, campus development officer, Swapnil Patel, sir, and also thank you to Dhaval Patel, sir, and for wonderful cooperation, computer HOD Meet Patel, sir, and HNS HOD, sir, Dr. Sanjay Taylor, sir. Last but not least, I extend my thank you to all the students for kind support. Thank you, sir. Thank you very
Okay.
much.
Sir, you can share my number also if they want to ask something.
Any
sure.
question to student?
Then they can share with me afterwards. You can share my number. Fine, sir.
Okay, okay. Anyone want to ask question from student side? Wait, sir.
Okay, okay.
Keshwani Ajit, sir. Wait, sir.
Yes, yes. Is there a difference between random experiment and samples? Yes, yes. It is a very much. They are both the things are two different things. A random experiment is a experiment that you are doing, whose outcomes are not known prior to doing that experiment.
Yeah, yes,
And
yes.
sample space is the outcomes. After means what are the possible, all possible outcomes. When you collect that, that will be the sample space. So they both have two different things. One of them is a set, one of them is a event. Yes. Anyone else, please?
Yes, yes, sure.
Yes. What is the basic difference between mutually exclusive and independent events? Okay, so this is a very nice question. Mutually exclusive, like I have told you while talking, that mutually exclusive events are like, say for example, simple example, exclusive showroom of Titan watches. Then whenever you go to that particular showroom, what happens is you will find out only Titan watches. They cannot sell any other brand. So that is called exclusive thing. And independent, when you talk about independent, is when two things are different. One of them cannot happen if other will, or other will not have any effect on that, whether second thing will happen or not. Like that another example we can give is, suppose I am selecting one card from a deck and I am rolling a dice. These are the two events. So see, suppose I get a king in this, what will have I have an effect on this rolling a dice? There is no effect. So this type of events are called independent. Yes.
Anyone? Very nice example, sir.
Arre. Always, always.
No one.
Fine. Later on, also they can ask. Don't worry.
Okay, okay. I will share your contact number. Okay.
Sure, sure. Sure,
Once
sir.
again, thank you, sir.
Thank you once again for giving the chances. Thank you.
Okay.
Okay.